Welcome to Artificial Intelligent Finances, the channel that explores the intersection of finance and cutting-edge technology. From machine learning to data analytics, we bring you insights into the latest advancements in financial technology and how they can help you make better investment decisions. Join us as we explore the future of finance, powered by artificial intelligence. ChinChilla AI versus Megatron Turing. ChinChilla by DeepMind. Researchers at DeepMind have proposed a new predicted compute optimal model, called ChinChilla, that uses the same compute budget as Gopher, but with 70 billion parameters and 4 times more data. ChinChilla uniformly and significantly outperforms Gopher, 280B, GPT-3, 175B, Jurassic 1, 178B, and Megatron Turing NLG, 530B, on a large range of downstream evaluation tasks. It uses substantially less computing for fine-tuning and inference, greatly facilitating downstream usage. ChinChilla showed a state-of-the-art average accuracy of 67.5% on the MMLU benchmark, a 7% improvement over Gopher. The dominant trend in large language model training has been to increase the model size, without increasing the number of training tokens. The largest dense transformer, Mount NLG 530B, is now over 3 times larger than GPT-3's 170 billion parameters. People also ask, can you, the public, use ChinChilla AI? Unfortunately, the general public cannot currently use ChinChilla AI, because it is still in the testing phase as of January 12, 2023. Once released, ChinChilla AI will be useful for developing various artificial intelligence tools, such as chatbots, virtual assistants, and predictive models. Now let's explore and look at what Megatron Turing AI is. Language modeling has been an active area of research for many years, and it has recently gained a lot of attention due to the impressive results that transformer-based models have achieved. This approach has led to state-of-the-art performance across a wide range of natural language processing tasks. DeepMind has also pursued this line of research and developed Gopher, a 280 billion parameter model that has established leading performance on a variety of tasks, including reading comprehension, question answering, and language modeling. In the last few years, the focus in language modeling has been on enhancing performance by increasing the number of parameters in transformer-based models. However, the cost of training these large models is high, making it crucial to find the optimal training setup to avoid wasting resources. The compute cost for training transformers is determined by 2 factors, the model size and the number of training tokens. The current generation of large language models has allocated increased computational resources to increasing the parameter count of large models and keeping the training data size fixed at around 300 billion tokens. This approach has led to impressive results. However, it is not the most efficient way to use computational resources. In this work, we empirically investigate the optimal trade-off between increasing model size and the amount of training data with increasing computational resources. Our main objective is to answer the question, what is the optimal model size and number of training tokens for a given compute budget? To answer this question, we train models of various sizes with various numbers of tokens and estimate the trade-off empirically. Our main finding is that the current large language models are far too large for their compute budget and are not being trained on enough data. In fact, we find that for the number of training flops used to train Gopher, a 4x smaller model trained on 4x more data would have been preferable. Based on our approach, we show our projections of the optimal number of training tokens and parameters in Figure 1. We show points representing the training setup of 3 different established large language models along with our new model, ChinChilla. We test our data scaling hypothesis by training ChinChilla, a 70 billion parameter model trained for 1.3 trillion tokens. While the training compute cost for ChinChilla and Gopher is the same, we find that ChinChilla outperforms Gopher and other large language models on nearly every measured task, despite having 70 billion parameters compared to Gopher's 280 billion. In Figure 2, we compare the performance of Gopher, ChinChilla, GPT-3, and Megatron Turing NLG for various common benchmarks, including question answering, trivia QA, common sense, Hella Swag, Pika, Winogrand, and Bulk, reading comprehension, Lambada, and the large multitask language understanding, MMLU, general knowledge benchmark. After the release of ChinChilla, a model named PAR-LM was released with 540 billion parameters and trained on 768 billion tokens. This model was trained with approximately 5x the compute budget of ChinChilla and outperformed ChinChilla on a range of tasks. While the training corpus is different, our methods do predict that such a model trained on our data would outperform ChinChilla despite not being compute optimal. Given the PAR-LM compute budget, we predict a 140 billion parameter model trained on 3 trillion tokens to be optimal and more efficient for inference. The results from our study show that smaller, more performant models can be more efficient than large models with high parameter counts. Smaller models also reduce inference time and memory costs, making them faster and accessible on less hardware. In practice, while the training flops between Gopher and ChinChilla are the same, Megatron Turing is a state-of-the-art language model developed by NVIDIA and published in a paper by its team of researchers in 2021. It is currently one of the largest language models in the world, with 530 billion parameters, and was named after Alan Turing, a British mathematician and computer scientist who made pioneering contributions to the field of artificial intelligence. Megatron Turing is a transformer-based model, which means it is built using a neural network architecture called the transformer. This architecture was first introduced in 2017 by researchers at Google and has since become the dominant architecture for building large-scale language models. The transformer architecture is particularly well suited for language modeling tasks because it is able to process and model sequences of data, such as words in a sentence, with a high degree of accuracy and efficiency. The development of Megatron Turing was driven by the desire to create a model that could perform well on a wide range of natural language processing (NLP) tasks, such as language modeling, machine translation, and question answering, while also being scalable and efficient. To achieve this goal, the researchers used a number of techniques, such as model parallelism, data parallelism, and mixed precision training, to optimize the performance of the model and reduce the time and cost required to train it. Model parallelism is a technique that involves dividing a large model into smaller sub-models that can be trained in parallel on multiple processors or GPUs. This allows the model to be trained more quickly and efficiently than if it were trained on a single processor or GPU. Data parallelism, on the other hand, involves distributing the training data across multiple processors or GPUs so that each processor or GPU can work on a different portion of the data simultaneously. This allows the model to be trained on a larger amount of data than would be possible on a single processor or GPU. Mixed precision training is a technique that involves using both 16-bit and 32-bit floating point numbers to represent the weights and activations of the model during training. This allows the model to be trained more quickly and efficiently while also maintaining a high level of accuracy. By using mixed precision training, the researchers were able to reduce the training time required for Megatron Turing from several weeks to just a few days. In addition to these techniques, the researchers also used a number of other optimizations to improve the performance of Megatron Turing, such as weight decay, gradient accumulation, and learning rate schedules. These techniques are commonly used in deep learning and are designed to improve the stability and efficiency of the training process. The performance of Megatron Turing was evaluated on a number of benchmark datasets, including the GLUE benchmark and the SuperGLUE benchmark, which are commonly used to evaluate the performance of NLP models. In these evaluations, Megatron Turing achieved state-of-the-art performance on a number of tasks, such as natural language inference, sentiment analysis, and question answering. Overall, Megatron Turing is an impressive achievement in the field of NLP and demonstrates the power of large-scale language models for solving a wide range of NLP tasks. While it is currently one of the largest language models in the world, it is likely that even larger models will be developed in the future, as the field of NLP continues to advance and researchers explore new techniques for building and training these models. Thanks for tuning into Artificial Intelligent Finances. If you enjoyed this video, don't forget to like and subscribe to our channel for more insightful content on the latest trends in finance and technology. We'll see you in the next video.